Hello friends and welcome to our lecture on energy flow in an ecosystem. To begin with, let me give you a brief outline of what we are going to discuss today. First of all, let us try to understand the fundamental concepts related to energy. Energy is defined as the ability to do work. The behavior of energy is described by two laws. The first law of thermodynamics, or the law of conservation of energy, states that energy may be transformed from one form into another, but is neither created nor destroyed. Light, for example, is a form of energy. It can be transformed into work, heat, or potential energy of food, depending on the situation, but none of it is destroyed. The second law of thermodynamics, or the law of entropy, may be stated that no process involving energy transformation will spontaneously occur unless there is a degradation of energy from a concentrated form into a dispersed form. For example, heat in a hot object will spontaneously tend to become dispersed into the cooler surroundings. In other words, because some energy is always dispersed into the unavailable heat energy, no spontaneous transformation of energy is 100% efficient. Entropy is a measure of the unavailable energy resulting from the transformations. The term is also used as a general index of the disorder associated with energy degradation. The transformation of energy through the food chain of an ecosystem is termed the energy flow because, in accordance with the law of entropy, energy transformations are one way in contrast to the cyclic behavior of matter. Moving on, let us now talk about solar radiations and the energy environment. The fate of solar energy coming into the biosphere is summarized in table displayed on your television screens. Although less than 1% is converted into food and other biomass, the 70% goes into the heat, evaporation, precipitation, wind, and so on. It is not wasted because these fluxes create a livable temperature and drive the weather systems and water cycles that are necessary for life on Earth. Energy flow in ecosystems begin with the capture of solar radiation by photosynthetic processes in primary producers. The accumulated organic matter, first as simple sugars, then combined with other elements to more complex molecules, represents the gross primary production in the system, some of which is released and used for the primary producers' growth and maintenance through respiration. The remainder or net primary production is available for the rest of the ecosystem consumers, including decomposers. Dear friends, let's now focus on energy partitioning in food chains and food web. The transfer of food energy from its source in autotrophs, that is, plants, through a series of organisms that consume and are consumed is termed the food chain. At each transfer, a proportion, often as high as 80 or 90% of the potential energy is lost as heat. Therefore, the shorter the food chain or the nearer the organism to the producer trophic level, the greater the energy available to that population. However, whereas the quantity of energy declines with each transfer, the quality or the concentration of the energy that is transferred increases. Food chains are of two basic types. Number one, grazing food chain, which starting from a green plant base goes to grazing herbivores, that is, organisms eating living plant cells or tissues, and on to carnivores, that is, animal eaters. Number 2, the detritus food chain, which goes from non-living organic matter to microorganisms and then to detritus feeding organisms, that is, detritivores and their predators. Food chains are not isolated sequences, they are interconnected. The interlocking pattern is often spoken of as the food web. In complex natural communities, organisms whose nourishment is obtained from the sun through the same number of steps are said to belong to the same trophic level. Thus, green plants occupy the first level, that is, the producer trophic level. Plant eaters, which are also known as herbivores, occupy the second level, that is, the primary consumer trophic level. Primary carnivores occupy the third level, that is, the secondary consumer trophic level. And secondary carnivores occupy the fourth level, that is, the tertiary consumer trophic level. This trophic classification is one of function and not one of species as such. A given species population may occupy one or more trophic levels according to the source of the energy actually assimilated. Dear students, let's have a brief outline of concept of productivity. The primary productivity of an ecological system is defined as the rate at which radiant energy is converted by the photosynthetic and chemosynthetic activity of producer organisms, chiefly green plants, to organic substances. It is important to distinguish successive steps in the production process as: number 1, gross primary productivity, that is GPP, is the total rate of photosynthesis, including the organic matter used up in respiration during the period of measurement. This is also known as total photosynthesis. Number 2, net primary productivity, that is NPP, is the rate of storage of organic matter in plant tissues that exceeds the respiratory use by the plants during the period of measurement. This is also termed as net assimilation. In practice, the amount of plant respiration is usually added to the measurements of net primary productivity to estimate gross primary productivity. That is, GPP, gross primary productivity, is equal to net primary productivity, that is NPP, plus respiration, that is R. Number 3, net community productivity is the rate of storage of organic matter not used by heterotrophs, that is net primary production minus heterotrophic consumption during the period under consideration, usually the growing season or a year. Finally, the rates of energy storage at consumer levels are referred to as secondary productivities. As consumers use only food materials already produced with appropriate respiratory losses and convert this food energy to different tissues by one overall process, secondary productivity should not be divided into gross and net amounts. The total energy flow at heterotrophic levels, which is analogous to the gross productivity of autotrophs, should be designated as assimilation and not production. Ecosystems and life zones differ in their net primary productivity as illustrated in the figure. On land, net primary productivity generally decreases from the equator towards the poles because the amount of solar radiation available to terrestrial plant producers is highest at the equator and lowest at the poles. In the ocean, the highest net primary productivity is found in estuaries, where high inputs of plant nutrients flow from nutrient-laden rivers, which also stir up nutrients in bottom sediments. Because of the lack of nutrients, the open ocean has a low net primary productivity. Let's now talk about energy flow modeling. A model is a formulation that mimics a real-world phenomenon and by which predictions can be made. In their simplest form, models may be verbal or graphic, that is informal. First, let us discuss a universal energy flow model. Universal model is applicable to any living component, whether it be plant, animal, microorganism, individual, population, or a trophic group. ODM depicted ecosystems as simple energy flow diagrams. For any one trophic level, such a diagram consists of a box representing the biomass or its energy equivalent at any given time and pathways through the box representing the flow of energy. The energy flow within and through a single trophic level is shown on the screen, in which the size of the shaded box is proportional to the total amount of biomass at the trophic level. Energy enters the trophic level when food is ingested by the organisms at that level. Some of the ingested energy is simply not used and is lost to the trophic level. The rest is assimilated. Some of the assimilated energy is required for respiration or is stored in the form of fat. The rest is used for growth or is ingested. The amount of energy or biomass that is available for the next trophic level is referred to as production. ODM's diagram may represent the dynamics of an entire trophic level or of a single individual within the trophic level. That is, the diagram summarizes the energy inputs and outputs of a particular individual or all of the individuals at a trophic level. Within a food web, there are a number of trophic levels linked by feeding relationships. ODM showed this in his model by linking boxes. Because energy is lost at each trophic level, successive boxes are drawn smaller because they will contain overall less biomass. For example, a box representing the predators in a food web will be smaller than the box representing the prey which are at the trophic level below the predators. Another model which needs to be discussed is Y-shaped energy flow model. In nature, we don't observe a single channel model of energy flow. It is a more complex flow of energy that involves grazing and detritus food chains. These are shown as separate flows in a Y-shaped or two-channel energy flow diagram as shown on your screen. This model is more realistic than the single-channel model because number one, it conforms to the basic stratified structure of ecosystems. Number two, the direct consumption of living plants and the consumption of dead organic matter are usually separated in both time and space. And number third, the macro consumers, that is phagotrophic animals, and the micro consumers, that is saprotrophic bacteria and fungi, differ greatly in size metabolism relations and in the techniques required for studying them. Moving on, let us highlight the ecological efficiencies. The ratios between energy flows at different points along the food chain are of considerable ecological interest. Such ratios, when expressed as percentages, are often termed as ecological efficiencies. The ratios have meaning in reference to component populations as well as to whole trophic levels. Lindemann laid the foundations of science of ecological energetics by considering the efficiency of transfer between trophic levels. In other words, percentage of usable chemical energy transferred as biomass from one trophic level to the next is called ecological efficiency. It ranges from 2% to 40%, that is a loss of 60 to 98%, depending on what types of species and ecosystems are involved, but 10% is typical. The more trophic levels there are in a food chain or web, the greater is the cumulative loss of usable chemical energy as it flows through the trophic levels. The pyramid of energy flow in figure illustrates this energy loss for a simple food chain, assuming a 90% energy loss with each transfer. Energy flow pyramids explain why the earth can support more people if they eat at lower trophic levels by consuming grains, vegetables and fruits directly rather than passing such crops through another trophic level and eating grain eaters or herbivores such as cattle. About 2/3 of the world's people survive primarily by eating wheat, rice and corn at the first trophic level, mostly because they cannot afford meat. The large loss in the chemical energy between successive trophic levels also explains why food chains and food webs rarely have more than 4 or 5 trophic levels. In most cases, too little chemical energy is left after 4 or 5 transfers to support organisms feeding at these high trophic levels. Finally, we will classify ecosystems based on energy. As we know, energy is the common denominator and the ultimate forcing function of all ecosystems, whether natural or designed by humans. It provides a logical basis for a first-order classification. On this basis, it is convenient to distinguish 4 classes of ecosystems. Number 1, natural unsubsidized solar-powered ecosystems. These systems of nature depend largely or entirely on the direct rays of the sun. For example, open oceans, upland forests, and grasslands. Number 2, natural solar-powered ecosystems subsidized by other natural energies. When natural auxiliary sources of energy can be used to augment solar radiation, the power density can be raised considerably. For example, tidal estuaries and some rainforests. Number 3, human subsidized solar-powered ecosystems. Human beings have learned how to modify and subsidize nature for their direct benefit, and we have become increasingly skillful not only in raising productivity but more especially in channeling that productivity into food and fiber materials that are easily harvested, processed and used. For example, agriculture and aquaculture. Number 4, fuel-powered urban industrial techno-ecosystems, which use energy from fossil fuels or other organic or nuclear fuels. Here, the highly concentrated potential energy of fuel replaces the energy of the sun. For example, cities, suburbs, and industrial parks. As fuel becomes more expensive, cities will likely become more interested in using solar energy. Perhaps a new class of ecosystem, the sun-subsidized fuel-powered city, will increasingly become a new category during the 21st century. It may be wise to develop new technologies designed to concentrate solar energy to a level where it might partially replace fuel rather than merely supplement it. That's all. Thank you.